Then I begin with this shorter presentation. It was also planned at the Egon Schulte's section. This is how to find fundamental domains for space groups. This is a joint work with István Prok, who is master in programming. I can tell you that we formulated general problems and gave general algorithm, but this algorithm is a super exponential complexity in general. That means then we have to reduce the problems, which are now a little bit attackable problems. István could solve these attackable problems, of course, and then we could find the result, which is concentrated, of course, Euclidean situation, Euclidean plane group and space group, and later for other spaces with the unified method just presented in the former presentation. That means projective geometric models help us to formulate all the things with linear algebra, of course, and the numerical solution could give us sometimes good things. And I can report very shortly some concrete things, but I've concentrated here some didactical examples. That means didactically easy things give us the situation. Pardon, what is the next? Pardon, thank you. Yeah, this is yeah, this is the point. Yeah. That means these are the general situation. I mentioned here this program, and I mentioned here also the collaboration. That means we solved the two-dimensional plane group very generally, originated by Quehenberger for hyperbolic plane group in the late 1900s, and then Zoran Lucic and Nebojša Vasiljevich were my partners to solve this problem, and I can tell you that Nebojša, as a good student and programmer, could formulate a program COM-class which give you all the plane crystallographic groups, fundamental domains. Of course, with super exponential complexity, but for easy things is not so complicated. But this is the problem circle here. I mentioned here that I just at the starting point, we worked together with Andreas Dress and Daniel Huzon, and we worked also in three-dimensional problems. We could determine all the possible so-called phase-transitive tilings in the three-dimensional Euclidean space. We found 88 such polyhedra in 7 families, which is not so easy. And I wrote also a very general formulation in this Acta Mathematica Hungarica, and with István Prok and Emil Szirmai, we classified all the simplicial space group, not only the Euclidean space, also in non-Euclidean spaces. This appeared in this Bolyai Memorial volume in 2006, It is a long paper, of course, with many tables and so on. And István Prok formulated also this general program. Sorry to say, it was not published yet in a larger spread journal. And now I start with the very popular Escher pictures for fundamental domains. That means you could see here these animals as fundamental domains, and you can study, sometimes the half of the animal is the fundamental domain, of course, and you could study different plane group for this situation, and you can study, of course, the 17 crystallographic plane groups, which very concrete examples. This is the 17 crystallographic groups, please. And this is the main point in that sense that we could have Euclidean tiling and we could have hyperbolic tiling. There is also spherical tilings with the same situation where we vary the parameters as rotational orders, then reflection corners, and so on and so on. You can see here also the notation of the groups. It is not so essential to turn here. And I analyze now for you this very simple situation. This is the tiling octagon and square, the Archimedean tiling, of course. And we could analyze the situation. First, we could see the very obvious reflections, line reflections. You hear M0, M1, M2, and the so-called crystallographic groups is P4M. Yeah. And then you could analyze, just Egon showed you, the so-called adjacency operations with dotted lines for the changing the vertices, dashed line changing the edges, and continuous line for the changing the domains, of course. Now we have two domains, the octagons and quadrangle, and we could have here also the very typical things, the so-called barycentric subdivision, to have the so-called flex structures, as Egon Schulte mentioned. A flag is characterized here by a so-called barycentric triangle, and barycentric triangle have so-called E0 vertex, E1 midpoint for edges, and two adjacencies for faces, of course. And at the end, not at the end, but this analyzing give you a graph, please. That means the barycentric triangle becomes vertices of a graph, and the adjacencies give us some edges, sometimes loops, and it is very typical for the next situation. This will be, at the end, the so-called Delaney dress symbol. I mentioned that Delaunay Boris Nikolaevich used this also, and nowadays colleagues use this also with other respect. Of course, the initiative was Andreas Dress and Delaunay, I think. This is why I call this D symbol, as a shortening and an honor for the discoverer. And then there is the algebraic description, this D symbols operator. That means the barycentric triangle will be formally reflected for the adjacents barycentric triangle. This is formally a so-called simplicial mapping. That means topologically and piecewise linearly. That means not metrically yet. Metric will come later. Whether Euclidean metric, whether spherical metric, whether hyperbolic metric. In dimensions 2 we have only these three possibilities, but you have to imagine that this machinery we can extend also to dimension 3 or more. Then we have more adjacencies. That means more richer graphs, colored graphs, and also more characterization for the adjacencies, which will be here the so-called adjacency matrix. This is in dimension 2, we have 3 times 3 matrices, just in the sense of projective geometry, and later it will be just the so-called formal Coxeter matrices and so on. That means we have a very nice theory which is very rich, and we could only indicate this. Now the indication here that we can change the parameters. Octagon was A equal to 4, that means 2, 4 is 8, of course. B is 4 for the quadrangle, the square. And then we can vary, and with octagon we can have decagons, and B were 4, then B is 3 is also possible. That means with different parameters we have different tilings, and then we have a very general method to construct also tilings and also groups, because the groups then depends on the reflections and the parameters, and this is also a geometric characterization just with the angle of triangle. If the angle of triangle is equal to P, then we have the Euclidean tilings, then greater than pi, then spherical, then smaller than pi, then hyperbolic situation, and this is a very general theorem. And now again the projective coordinate system. That means first we have this plane situation for the triangle here. Pardon, I couldn't see, but no problem. I can tell you the triangle there. This is an outer point for the origin, projective coordinate system. And then we can define plane, point, vectors, and forms, and so on. And we could define the reflections. Reflection will be also then matrix, of course. And then we could, this is pointer there. Thank you. Yes. This was the projective plane and the triangle before, and this is the coordinate system. Vectors for vertices, plane, that means form, linear form later, and this is a very nice linear algebra calculus for the next situation. And then you could see the formal structure here. Please, it is a very useful linear algebra, of course, and we have here the matrices for reflection, M0, M1, M2 for the former reflection, with free parameters, that means unknown parameters, which will be determined later depending on the defining relations. Please, this is the machinery, how to work the matrices, and this is the product for the later power. And now this is the last result. That means this M1, M0 depends on cosines matrices, and ABC as pi over A, pi over B, and so on. And then we have the characterization with spherical, Euclidean, and hyperbolic situation, and it's very characteristic. This is the so-called invariant scalar product for later. And if we consider the quadratic sums for this bilinear form, that means the quadratic form, that means then that this last term here, this sign is just depending on the angle sum here. That means if angle sum here give us a positive sign here, then we have plus 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 signature for spherical group. If it is 0, that means the angle sum is pi. It is 0, then plus plus null, it is the Euclidean signature. And if the angle sum is smaller than pi, then this is minus, and plus plus minus characterize the hyperbolic plane. And this is the general things. And I can tell you that the machinery is just the same in higher dimension. Also in dimension 3, with some modification, of course. Modification is very strong, which is why we haven't any complete classification yet for three-dimensional situation, but this is very important. And this is only the picture for the the decagon square for hyperbolic plane. And this is now the three-dimensional case, also relatively easy things, but not only reflection, we have also half-turn for the simplicial situation, please. This is the simplicial situation, and this is relatively well-known crystallographic groups, the the so-called trigonal group here, please. Yes. And then you have here also the half-turn axis and the reflection plane. And then we have the same machinery, but we have here the adjacency matrix one H more here, and again the matrix. This is just the same as the cube matrix. This is why this is a parallelogram lattice, it is a cube lattice, and these pictures here give us the complete information for the later situation, but it's very important things here, please. We have this situation where the former tetrahedron give us a hyperbolic base here, please. This is the angle sum is smaller than pi. That means we have here H2 cross R group. If the angle sum would be greater than P, for example, A equal to 3, pi over A, then P, and so on, then we could have also spherical groups and other things here. That means depending on the parameters we have different groups, and again the Thurston geometries. And I mentioned here some results, characteristic results. This is also a general paper for crystallographs for so-called day symbol method. Yeah, and Acta Crystallographica appeared. And this is our classification work with two H-transitive tilings for Euclidean, non-Euclidean planes, of course. And this is the for a three-dimensional situation with my colleagues Lajos Borodsky and Rita Kós with the adjacency variation. Here is Lajos-Borowski result for the H-transitive three-dimensional tilings. Sorry to say, it is very much. And no, you see here only one red line, which is Euclidean. All the others are non-Euclidean. That means if we have 88 tilings by this former classification, then we could have more than 3,000 cases for H-transitive tilings later on. And this is mentioned here, the plate with Andreas. And this is all phase-transitive and H-transitive situation with figures, please. We have 7 families for this nice Euclidean polyhedra, and you have to consider this as a space tiling. And there is an axiomatic theory for this. I mentioned here this nice actions formulated very shortly and very condensed, because we have only 5 actions, and depending, of course, the things. And this was the first paper with István Prok, just appeared in Vienna, here, 88. And this is my paper in Acta Mathematica Hungarica, a 40-page paper, of course. From this, there is the flex structure, as Egon Schulte mentioned. This is the classification for plane, and this is the theory, how to define these groups and the so-called cycle relation. This is also for the cycle relation here. And this is some so-called manifold structure. That means for smaller domain, we can glue together such a structure where all the points have ball-like neighborhood. That means this is the spherical manifold of Strelfall, and this is just my presentation, the Fullerene, please. This is the typical Fussball manifold in hyperbolic space, and this is just the Fussball structure, which fill out the hyperbolic space. We have also other possibilities and also others. And this is a very general method for this classification strategy. And this was just the joint presentation with Zoran Lucic and Nebojsa Vasiljevich is just under publication. Egon Schulte knows this better. This is the two-dimensional description for this and this is the Euclidean specialization here. And I think my time is over, and thank you for your attention.
Leave it up.
Thank you. Also now I give you this because Renate. So. Dear colleagues, we are after time, but if one question would be useful for you, I suggest which time Renate is preparing here. If you have, then, and I am ready, of course, for conversation also in the breaks and also later on. Yeah, not then. Here. Then I'm ready. Preparing then, we are, as I know, we have time enough for next program, evening program. That means please we listen to our host. presentation. Renate Quehenberger is just the organizer of this conference, and as I know, pardon, her presentation is also very interesting. Yeah, and she wrote also a very nice book. Yesterday she was celebrated by this edition, and I wonder, always I can tell you that I could study a little bit this word a bit earlier, that artist, she's an artist,
Careful.
how to
Careful.
use the five-dimensional concept and five-dimensional geometry for some artistic and mathematically, physically, and so on interesting phenomena. Yeah, please, Renate, if you're ready, then we can continue.
Thank you very much for this nice introduction.
There's usually, where's your system
No, it is your race, of course. But I mentioned only that I was the laser chairman. Couldn't stop myself.
You switch it to my machine. No, oh, no, wait a minute.
Excuse me.
Do you have your presentation?
Yes, went by some steps.
Oh, I see.
Stems, but I saw they have, so I asked, but they have only up to 8.
Yeah, that's right.
The more. You want to do the media market or what?
Oh, that's right.
Or what is it? Do you want to buy it?
Where your accounts?
So I can't. I will go with my bike to the media market and buy one for you. 64. If they have.
I have a nerve function.
After the lecture,
You can drag your movies.
I have some time and then I will go.
You have a unlimited slash.
Yes, if I get one, the 64. And if they don't have
If you need it,
do you know how much one costs? Yes, I will. I can pay István.
No, let's just transfer everything to the flash drive.
These are like mirror stuff, no?
Yeah, I have mirror stuff on here.
Which is mirror stuff?
Well,
Probably here also
on here.
Yeah.
Like on the yes, like this.
It's probably one of these. I don't know, it's probably one of these. How do you
Maybe. It should be under system preferences. Normally it's under system preferences. And that would be under displays. System preferences, displays. You got it?
What?
We just plug the program. And you can use this as a point. Or he has maybe.
Thank you very much for your patience.
Yeah, Mano, maybe I introduce you again, but now the title is there, please, and please Renate then for the presentation.
So thank you again for the patience, and I hope I can tell you something about my visualizations on unifying series in 5 dimensions.
Phase space. Hilbert space 1. Hilbert space 2.
Banach space.
Minkowski space.
Riemann space.
Compact space.
Connected space.
So this was one performance with Peter Weibel. We were just counting different spaces, and now I work with hyper-Euclidean, and it's the short overview shall tell you. I will speak about the short introduction to a 5-dimensional unifying series and the visualization and how it refers to the Poincaré homology, sphere, Kepler, Plato, the golden ratio, and iter. And so 5-dimensional series played an eminent role for the unification of the elementary forces over the past century, but possibly due to the missing physical interpretation and or descriptive geometry, it is not fully understood. Here, a visual geometry shall be described for different concepts by Nordström, Kaluza, Klein, and later attempts by Pauli, Jordan, Einstein with Meyer, and Bergman, which remained unsatisfying. So even before the general relativity in 1916, Nordström was unifying all then known forces with Einstein equations and Maxwell equations involving the construction of a 6-vector and a 4-vector, which was then a 10-dimensional space, for which we also understood that the ether is the ontologic system. And he showed that the treatment of the electromagnetic field and the gravitational field is possible if one understands the 4-dimensional space-time as surface laid through a 5-dimensional world. And similarly to this, also Theodor Kaluza made his attempt in 1919. But before I can switch to Oskar Klein, 1938, where he unified the he already tried to present a unified model of electromagnetism and nuclear forces based on U1 gauge theory of isospinors. And he almost constructed a U2 gauge theory as David Gross claims. And the grand unified theory by U1 gauge theory was only achieved in the standard SU2 as U1 model of electroweak interaction in 1974 by Georgi and Glashow 1974. And after that, in the 70s, string theorists rediscovered Kaluza and Klein, and they connected with the five-dimensional series and extended them to higher dimensional series, like up to 27 dimensions. And it was also Wolfgang Pauli and Jordan who further developed the relativistic field series, which then led to quantum electrodynamics in the late 20s, and this also influenced Dirac to propose the relativistic theory of the quantum mechanics. But I think it's a little bit confusing. But yeah, the starting point of relativity we can see clearly in Poincaré 1902. There is no absolute space and we only perceive relative movements. And he said there's no absolute space and no absolute time, which very much influenced Einstein. Excuse me. But what does five-dimensional space look like? We have then these sketches, always like rolled up circles on a grid. This is also due to Klein, who was thinking with Kaluza about how to treat it geometrically, and he found that it can be seen as a cylindrical entity which is rolled up in a tiny circle and even measured the diameter. So this is what I wanted to show you before. This is the Kaluza theory, where Einstein was so kind to present it to the Prussian Academy of Sciences in 1921. It took him only 2 years to think about it, if he should do it or not. And after that, 1927, he was also replying to this to Kaluza's idea. And before he wrote to Lorentz that Kaluza already approached the perfect union of gravitation at the theory of Maxwell in his five-dimensional theory. There have been many attempts to retain the essential formal results obtained by Kaluza without sacrificing the four-dimensional character of the physical space. So this was very important for Einstein to keep his four-dimensional world as it is and not disturbed by five-dimensional theories. And then also that he says but to assign it to some physical meaning. This was also the motivation to write the article in 1936 then later. And he's also referring to the cylindricity by the assumption that space is closed or periodic in x to the power of 5, which is then Klein's assumption of the small circle. And of course we have then in the relativity theory the term where x to the power of 4, excuse me, that's a mistake, is c times t, which means that time is multiplied with the velocity of light. And this, we all know it works perfectly for the GPS, but in fact it's just a measurement of the signal of light. And it's not what is useful for, or what we are affected in our daily lives. I mean, if you think about time in 4 dimension, then we found this other depiction model. We put the tick of the zigzag of the signal as a time on a circle. And this circle is then embedded in the 5-dimensional space in the Penrose pattern. The Penrose pattern serves as a basic model. The Penrose pattern, which is also the pattern of the golden ratio, and known as a 2-dimensional slice of the 5-dimensional space. So we have this grid space model. If we take all this, the lines, grid lines of the pentagrid, and also wrote an article to compare it with the Calabi-Yau manifold, which is also a 6-dimensional space, where they just neglected, they put 2 coordinates to 0 to make this unfolding, while the quantum cinema model is then stretched out. So, and then to explain how it should work for the real world, then we would have then this 4-dimensional Stangen space with the moving spaces and the small circles for the 5-dimensional space. And we have the references to Theodor Fechner and Balagi, and there is also possible to apply the electric magnetic forces to visualize the magnetic forces by small circles, and the electric force by the straight grid lines. And then it becomes obvious how Maxwell's theory can be embedded in the 4-dimensional case. Or to see then how the Lorentz-Poincaré transformations can be applied in the pentagrid, it would then be also this counter movement of the 2 spheres which are embedded into each other. And this is also something what Lorentz describes very detailed in the theory of the electron, 1916. And this is also something that I would like to discuss with you, because as I understand, if you understand it right, you can also see that the Einstein notation is then equivalent with the principle of what he also says, of course, that relativity theories according to the Lorentz transformation, that we can take instead of A and B, like the description of Weil, 1927, we can put this instead of A and B, G plus, and then perform the imaginary movement. And also there's a similar picture for the quaternions, and the moving spaces and the flowing spaces of the of Melchior Balagi is then the inspiration for the visualization. And we have also to see that Theodor Fechner was first explaining the 4-dimensional space in 1845, and now it's more than 150 years later, and we still don't know how to cope with this imaginary factor of time. And so here we try to visualize this counter movement of the spheres, and that which are then represented by circles, and the overlapping of the circles where then light would appear as electromagnetic disturbance. This is a very simple preliminary picture, but I should explain this five-dimensional axis. And also these grid lines, what we saw here in the space, discrete space model, is also something what refers to Maxwell's preliminary idea, the fundamental idea of the eta as the ontologic system which provides the possibility of the electromagnetic phenomena. The concept of Maxwell and Faraday implies force fields or magnetic lines of forces independent of matter. And he described first the presence of electricity as a disturbance and light as a disturbance of the electromagnetic field. What then later Kaluza and Klein said it's the electromagnetic field disturbance in five-dimensional space. But this is still all the Maxwell equations, both Maxwell equations are based on the idea of the eta. And this is maybe going too much into detail if we ask about the difference about special relativity and Lorentz transformation, but maybe we could, this is something what I mentioned before was what we can discuss hopefully later. And so let's come to the final visualizations about five-dimensional space, and we can recall Henri Poincaré that he considered five-dimensional space from the viewpoint of analysis situs as appropriate for group operations applied on a space which works like a machine. And so here this space would then be formed from the three-dimensional space cells of the three-dimensional representations of the Benmo's kites and darts pattern, which is then forming the three-dimensional dodecahedron and also the four-dimensional dodecahedron. And if we put them, the mechanism of this was music of Ben Skepper. This is also in the exhibition. This is actually the idea of Henri Poincaré applied on the space, the description of the homology sphere applied on the four-dimensional dodecahedron. And what you see is the pattern which is evolving. You can have it, and also here we see if it's like working like a machine, you can really cut it into smaller parts, and each point of the space you can apply another group operation, and then you would have this space which is on each point in space. We could have then this arrangement of the intersecting epitahedra, and which seems to form this stability, and which seems to be relevant for quantum mechanics because it's also representing the 24-dimensional space, if you want. And or like you saw here, the pattern which is evolving with the transformations. Or we use it also like for some first steps to visualize genetics, because the three-dimensional representation of the Penrose pattern is useful to visualize hydrogen atoms, because hydrogen is known to exhibit the symmetries of the Penrose pattern, and so this three-dimensional version it would give us a hint of what's going on. If you saw it, it's also possible to close the to imagine this is this zip effect of the double helix. But you will see it later. Hopefully, you will come to the concerts in the Collegium Hungaricum, or like this. And there would be also another movie where you can see that it's possible to apply the group of rotations in the icosahedron, and you can find different patterns. And of course, this is very on the first step of the development of a new geometry. It would need a lot of interested, very good mathematicians like you all here to further develop this first stages. And now I can show you this a short movie about the idea of Poincaré for the now we need rules, but maybe it's not so necessary. I explained it to you already. And we have sound. So this is how the four-dimensional space, the four-dimensional dodecahedron is formed by 12 of these three-dimensional representations of the Penrose kites and darts, and then forming this rotations, with the counter rotations, we can really see the transformations in steps of 36 degrees. And this is actually what Poincaré wrote in 1905. So this is something what I would like to discuss with you. And for me, this already shows that the five-dimensional space is appropriate to embed the four-dimensional stuff what we need with electromagnetism and so on, and also this goes to the structures of the quantum world. It's just dodecahedral universe, I think. And of course, if you think of Plato, then we have also this the notion of the fifth element, which is named quintessence by Aristoteles, and which is synonymous for the ether. So what we see here was the five-dimensional space, which works like the ether, and which is also which satisfying the mathematical space for group transformations which we need. And also, I know ether is not modern in this time, but it's very controversial, because also Einstein was very unsure about its existence, and he changed his mind during time. And physical space and ether are only different terms for the same thing. Fields are physical states of space. This is what he also claimed in his last book, I think, what he first wrote in 1943. And so this makes then also a sense to connect the idea of the field to ontologic space. So what is the conclusion and discussion which I like to have with you if you have still time, but maybe it's better we go to the concept team. So if we can embed, just use the Lorentz transformation and embed it in the five-dimensional space, while we need this discrepancy between relativity theory and quantum mechanics is my question. And isn't it enough what Poincaré gave us already, all the tools for the unifying world view? References from this acknowledgements for the Bantu Cinema project, which enabled to produce these movies. And I also thank Professor Rauch, who will be in the panel on Friday with me. He was a very nice discussion partner for all these tasks. Samsonov, Blüminger, and Peter Weibel, and Helmut Starke, who is also here at the TU. This was the Kanto-Cinema with Peter Weibel. Thank you. Thank you.
Maybe you could give some more light. Ready? Yeah, question please before the nice evening. Some theory and some visualization here. Yeah, Renate, my question. Pardon. Yeah, thank you, Professor.
Another question. Are you proposing a three-dimensional? I don't understand the physics part of it, but question on the geometry. You're showing the three-dimensional objects. Are you proposing that they are the equivalent of the kite and the dart in 3 dimensions, and they fill space aperiodically, forcibly?
Yes. And at the last symmetry, I had a conversation with Koji Miyazaki. I'm glad that the last symmetry 3 years ago, I had a conversation with Koji Miyazaki, who was first drawing the 5-dimensional cube, and he was looking at it, and then he came to me after 2 days, and he said, now I understand. This is you're a genius, he said, but he said, this is what you saw here, this 4-dimensional dodecahedron, which is filled with this 12 epicahedra. This is actually the infinite 5-dimensional space, which has the border of dodecahedron. The border is in the shape of the dodecahedron, analogous to the Penrose pattern in the 2 dimensions, which have either pentagonal or decagonal borders. So, and this is for me a very fascinating idea. This makes them also possible that you can cut it on each point where the lines are meeting with the surface,
so
and you can make smaller and smaller parts and going up to higher dimensions.
So that means if you take your modules, I think they're outside,
Yeah.
if you pack them together physically, build them physically, you pack them together, you take a slice through it perpendicular to the 5-fold axis, you will get the kite in the dot pattern?
This happens actually with the hypercube. Yeah.
No, in your case.
In my case, it's then again this dodecahedron. I did not. There are different things where you cut it, like you can assemble it to inside the icosahedron and you get a great dodecahedron. But I did not get exactly the petals pattern with one cut. No.
Please, Professor.
Let me expose my ignorance. Can you identify 5 dimensions with the x, y, z, t, and fifth? And what would that fifth be?
Yeah, this is what I was showing at the beginning in this pentagrid, where maybe I can go back shortly. This. So and then we have again in this we have the grid, pentagrid, and we would have the 4-dimensional space around the sphere, and like a tangent space, and then the small circles where the overlapping from the big circles which are symbolizing the 4-dimensional space.
You can visualize your 5th dimension, but what I'm asking, is there any physical meaning to each of the 5 dimensions?
Yes, like
and if they do, obviously x, y, z will take care of 4, but what takes care of 5th?
So this is different, like Kaluza starts with G0 to G4, and this was also the problem why Einstein took it up again. He said maybe there is, he wanted to examine also the physical meaning, but for me it's quite clear. We have the 3-dimensional space like here, but we have time, so we move, but we have in the impression the space is still the same, but it's not. It's moving. We were moving, but so this is the imaginary movement what we have, what Fechner described. And then we have light, which is the propagation of the turbulence of the electromagnetic field in 5-dimensional space. And then we have then beyond this 3D world all this particle space.
Very small remark. So thank you very much for so interesting talk.
Thank you.
So I only knew about Kaluza Klein, that's all what you say. But I want to say that there are people who generalize Penrose in 3 dimensions. It is actually kite, both things are zonotopes. And there are 3-dimensional zonotopes and even more. So mathematically, polyhedral theory knows some other generalization of Penrose styling. That's all. Just small remark.
Thank you.
As I know, but Renate mentioned this higher dimension projection, how to derive this Penrose style by higher dimensional projection.
Quasi-crystal,
Yeah.
yeah, from pentagrid. It's one way, but also you can generalize it.
Yeah.
Again, as a biologist, I came to the conclusion that to explain life, we need that 5-dimensional space. And I published this 10 years ago. And there, I identified the 5th dimension with genetic information. I'm just wondering whether it's related to what
This
you're
is
doing.
interesting, but I'm just developing this concept from Euclidean geometry, like space and moving spaces, nothing else. So this is just lines and points and planes. No, just geometrical elements. I would not
Can you
mix it with...
Can you attach something to memory, for example, in your geometric visualization?
Only points and lines. I only think of in terms of circles and triangles and platonic. Thank you.
Is there question more? Thank you, Renate. I would like to thank you for your enthusiastic discussions, and of course we deserved nice music, and please continue also this evening.
Yeah, please come to the Kollegium
Before we would leave the room, please, just 1 second. I would like to call your attention to a miracle which happened. This just started during the General Assembly, but I'm sure that you were very busy. But during the General Assembly, something started to flourish here from the table.
Then I begin with
of the lecturing table, and when you were introducing for us this wonderful higher dimensions, this beautiful three-dimensional example of symmetry, it just flourished more and more intensively towards fifth dimension. As I see, it grows towards the fifth dimension, and with this we would like to say thank you for all the work you have done for us. Thank you very much. And one more thing, that we were talking a lot about Renate and also about another person, Wolfgang, during the general session, and the miracle is just symmetric because Wolfgang is also happened to arrive from Hanover, so the flower is for Renate and the pleasure is for Wolfgang, so this is the share. Thank you very much.